So far, we are discussing about the option of having a specific matrix, which could be something like 5 minus 3 minus 3, 5, and this could be in the standard basis. And then we have the option to go to a new basis, which could be B1, which is composed of vectors of 3, 1, 5, 2. For example, here we have the new basis, and we know that these vectors, which constitute the basis here, this can be used as a transform from basis B1 to the standard basis. Let's call this one the standard basis. And then we often know and we said that we can use these vectors to transform any vector x in the basis B1 and any matrix D1. We can see how this can be projected. So here we have the vector x in the standard basis. This is the matrix P. We can come backwards with P inverse and so on. And we have two types of transformation. The first one is the transformation of a vector. So if we have a vector x, which is in the basis B1, if we multiply this with the matrix P, we get the vector x in the standard basis, okay? So we should know as a procedure that we need to multiply any vector only with the matrix P. But then, if we want to transform a linear transformation, so we can call this one vector transformation or vector reprojection. This is what we do for vectors. And for the linear transformations or for the matrices, what we need to do is that we're going to use the following: P inverse times P times A times P. These are all matrices, and this would be equal to a new matrix D. Okay, so this is linear transformation, change of basis, linear transformation. And we know that with linear transformation, any linear transformation, it can be represented or is equivalent to some matrix which can be carefully defined or carefully determined. So this one, we do remember it from the last time. And from the most general definition, we know that any two vectors which can be described by this relation, we call these two matrices similar matrices. So D and A, they are defined as similar matrices, okay? And within this discussion, we may want to, so let's assume that we can have another matrix which can be 3, 5, 1, 0. So here is another matrix. I believe you can see that. And we may want to find the best correspond to this matrix here. Okay, 5 minus 3 minus 3, 5. Then let's come up with 7, 2. What is this? Sorry. Let's assume that in the standard basis we have a matrix A, which is 5 minus 3 minus 3, 5, and another matrix B, which is 7, 2, minus 15, minus 4. So here we have two different matrices according to the best standard basis. And then let's assume for a moment that we want to describe the first one in a different basis. So let this correspond to matrix A, okay? And then we want to find also a good basis. Let me find some space. Let's use here. Let's try to identify the best basis for matrix B. Okay. So then we have to look for two different ones, and then how can we do this? We mentioned from the last time that given any matrix A, we have to find the eigenvalues, which are lambda I, These are eigenvalues, and also eigenvectors, vectors x, eigenvalues and eigenvectors. And in principle, the eigenvalues and eigenvectors, they are both equivalent, okay? So I've had some questions that come from the students of the type that they say that the eigenvector depends on the eigenvalue, okay? I believe we cannot say it like this because they are both equivalent. They are strongly dependent with respect to each other. And regarding this, I mean the following. This is not a true picture. This is wrong, okay? So I'll try to draw this one. When I say wrong, I mean it's conceptually wrong. It's not that we find, so this is in principle wrong. What is more correct is this picture. Given a matrix A, we find lambda, and equivalently we find this. So this is a more acceptable picture. Or if we use the hierarchy of principles or of quantities, this is the A, and down here we have lambda and x. Okay, this one might show only the way how we find eigenvalues. So first, how we find eigenvectors. Somehow we have to find first eigenvalue, okay, because that's the order of the operation. But this does not mean that x is a function of lambda. Rather than dependent from lambda, they are associated with respect to each other. Okay, so probably these two pictures are more clear into providing the understanding of what is the lambda and the x. Now, regarding these two examples, let's try to identify now how we can find the best basis with respect to the standard basis if our data is represented by the matrix A. So always the path that we need to work with is that we have to use the eigenvalue equation. So here we have lambda x, okay? And as we said the last time, this equation, this can be written as A minus lambda I times x. This is a vector. This is 0 to another vector. So, and then the x is different from 0. X is non-trivial solution only if the determinant of A minus lambda I is equal to 0. So this is A minus lambda I is equal to 0. So the general picture is this. So we can read this in a second. Let me take this away for a moment. So this is which should be in our mind. And let's try to solve these systems for both of these two matrices. Let's pick the 5 minus 3 minus 3, 5. So if we pick the first matrix, we have the following. This is 5 minus 3 minus 3, 5 minus lambda times 1, 0, 0, 1. And this is equal to 5 minus lambda minus 3, 5 minus lambda. So here, this is the matrix which we denote this one as A, matrix A, minus lambda times the identity matrix. Then the determinant of this expression is equal to 0, where we have that 5 minus lambda all squared plus 9. This is equal to lambda squared minus 10 lambda. Well, wait a second, is this plus 9? Somebody can help me here? This is minus 9, lambda squared minus 10 lambda, plus 25, minus 9. This is equal to lambda squared minus 10 lambda, plus 16. This is equal to 0. Okay. So, given this expression, we notice that we have to deal with a polynomial in, so this is a characteristic polynomial. So let's write this one, characteristic
We factorize it with -8 and -2.
We should also consider that the number of eigenvalues will be equivalent to the number of roots to our polynomial.
You mean the number of eigenvalues? Yes, I think we can say that is true, because this polynomial, what is the order of this polynomial?
Square.
Second order polynomial, so in unknown variable lambda. So this is a P2.
And we will expect two roots. So two eigenvalues.
That is true, because from a 2 by 2 matrix we get the second order polynomial. That is true. So what could be the roots of this system here?
Lambda -8 times lambda -2.
That is true. So this means that we can obtain that lambda 1 is equal to 2, and the lambda 2 is equal to 8. So then we found the eigenvalues, and given the eigenvalues, we can try to identify the eigenvectors. And the eigenvectors, we have to identify them as follows. So here we have the matrix, it's 5, -3, -3, 5, times an eigenvector, which has to be 2 by 2, and this is equal to 2 times
2 multiplying AB.
That is true. So what equations can we get from here?
5a minus 3b equals to a, and minus 3a plus 5b equals to b.
So how many equations do we have?
I can say that we only have one equation, because the second one we can omit it and we can work only in the first one, because the second equation is clearly independent from the first one.
That is true. So the second equation, it is linearly dependent on the first one. So from here we get that we have 3a is equal to 3b, right? Yeah. So
yes, and we can say that we have an infinitely number of solutions, but we should also consider the lambda 2 value.
That is true. So here we can get a pair of AB, which is going to be equal to 1, 1. Okay, so this is a pair of numbers. So which means that here, in this basis, one of the vectors, it is 1, 1. Okay, which will serve as a basis of the of this new domain. So let's try to identify the same expression for lambda equal to 8. So instead of having here 2, let's put here an 8. Then here we have 5a minus 3b. This is
8a.
8a. So then what is the next equation?
Minus 3a equals 3b.
So what is a pair of a and b? The pair
1
of a
and minus 1.
That is true. 1 minus 1. So this would be the second vector, which can help to define a new basis. So if we are to draw this pair of vector, I believe you can see this part. So 1, 1 is this vector here. 1 minus 1 is this vector here. So these two vectors, they can be used to describe the R squared. What was the standard basis? The standard basis, it was 1, 0, 0, 1. So there are two vectors that are shown here in red. Okay, I believe you can see that, or we can do a better job with this, which would be the following.
To find the diagonalized matrix, I think we can write lambda 1, 0 and 0 lambda 2. And we can just substitute the values that we found at the equation.
To find
which means the diagonalized matrix, we can write 2, 0, 0, 8.
That is true. So here we can get the diagonal matrix, which is 2, 0, 0, 8. And now, similar, so this is for matrix A, this would be the respective basis over which we can easily diagonalize the A into D, like this. Then we can try.
Or we can also prove it by finding P and P inverse and multiplying it with matrix A.
That is true. So this means that wait a second. So these are similar matrices. We mentioned these arguments. So here we can say that in this stage we have P. It's equal.
P inverse multiplies.
This is P. P inverse is equal. What is the determinant of P?
-2.
That is correct. This is
We exchange 1 with -1, and we change the
signs here, I believe, right?
yes.
Okay. So in this case, if we have to multiply the P inverse with A and the P again. So here we have P inverse times A times P. This would be equal to -1/2 times -1 -1 -1 1 times the A, which is equal to
5 -3 -3 5
and 3 5. And then we get
times 1 1 1 -1.
okay. So we can check the necessary steps and check what the results or what the result will finally be. And in a similar way, we can also have a look at the other matrix, which is here the matrix B. And in this case, we'll have the 7 2 -15 -4 times AB. No, we shouldn't do this yet. We are still in the first stage because we have to subtract from here the lambda I. And if we subtract here, so we are in this step here. So in this case, here we'll get
7 minus lambda, -15, 2, and -4 minus lambda.
Then the polynomial here, it's going to be the 7 minus lambda.
Second grade again.
That is true. Here we get plus 30.
So we will accept 2 roots or 2 eigenvalues, lambda 1 and lambda 2 again.
What is the polynomial that we get here? This is -28.
-7 lambda plus 4 lambda plus lambda squared.
-4, so plus 4 lambda. Plus
Lambda squared
plus 30
plus equals 0.
0. So here we obtain the following. We have lambda squared minus 3 lambda plus 2, we get a 0.
We can factorize it, lambda -1, which multiplies lambda -2, and we get 2 eigenvalues, which are 1 and 2.
1 and 2. Now we could immediately expect the following. So here we can have the diagonalization of A. We can denote this like this.
1 0 0 2.
So let's assume that this is a diagonalization of B, which is 1 0 0 2.
But we have to prove it by saying that B equals P inverse A multiplying B. We have to prove that the diagonalization of that matrix is that.
So how can we find those? Then we can simply report we can try to find the eigenvectors by
equals 2AB. For the second, I was saying.
AB. So what would be the first equation?
7A minus 15B equals A. And the second will be 2A minus 4B equals B. But similar to the first case, I think we can omit the second equation because it's linearly independent from the first one. So we can just continue the interactions with the first equation. We have 6A equals 15B.
That is true. So then we get the
5 and 2. 5 for A and 2 for B.
What is this? 5B. So this would be the case for the first eigenvalue. So we find AB would be 5 and 2. So here we get 5 and 2. And for the next eigenvalue,
we can just substitute. We can put 2a.
Yeah. So in this case, the second set of equations, it will be 7a minus 15b. This would be equal to 2a.
And 5a equals 15b.
So in this case, we can easily predict that this could be a 3, and this could be a 1.
So 3, 1, the second eigenvector.
Okay, so this is how we can try to identify the new basis for the matrix A and for the matrix B. So apparently we need these two bases, where for this one we're going to move this way with PA, and for this other matrix we're going to move to using the PB. And PA and PB, this would be because we use this notation, this will be PA, and PB will be this matrix. Okay, so for what we did, so this is how we can identify the best possible basis for respective matrices. And these were matrices which were 2 by 2, and the eigenvectors, they are vectors which belong to the null space of this matrix. So we have A minus lambda I times x. This will be equal to 0. So the null space so actually all of these vectors that we see here, all of these two here and these two here, they are all representative of the null spaces. So if we ask the following question, what is the dimension of the null space of this matrix when lambda was equal to, let's pick one case here, was equal to 8. So when lambda was equal to 8, what is the nullity of this matrix? Who can answer this? I can pick someone. If you want, you can raise your hand in the comment section. Who's not great door? Ari, yes, Ari, you can answer this. So, what is nullity, Ari?
It's 1.
It's 1. Why is it 1?
Because since we have a matrix with 2 dimensions, with
Yes.
2 vectors, and we have 2 eigenvalues, it corresponds to one vector for each eigenvalue in the null space.
That is true. And also, we can also say the following. So the nullity for each eigenvalue, the nullity will be equal to the number of free variables, okay? The number of free variables, when we're trying to solve this system that we see here, this is going to be, so for a moment, let's assume, allow me to take out this part, and we would have, what is A minus lambda I? Lambda is equal to 8, so here we'll have 5 minus 8, this is minus 3, minus 3, minus 3, and 5 minus 8 is again minus 3, okay? So this is the matrix, and now this matrix, the reduced row echelon form is going to be the following: 1, 1, 0, 0. Because so here we have one leading one, and we have one free variable that we're going to consider this one S, right? So if we have only one free variable, we consider that we have the dimension of the null space will be equal to 1. Okay, so if we see this example here, it looks like the nullity for each of the eigenvalues that we see here on the board is always equal to 1. So let's have a look. What eigenvalues did we have? We have here lambda 1 is equal to 2, Then this was 2, this was 8, here this is 1 and 2. So these were the 4 eigenvalues. Individually, all of those can construct a matrix A minus lambda I, where nullity is all equal to 1. Now, the concept of nullity, or the concept of the dimension of the null space, which corresponds to each eigenvalue, this is important because it can constitute the eigenspace. Now, the eigenspace, this is a definition which can be associated to one specific eigenvalue, and it is not always going to be equal to 1, because there could be some cases where the matrix A is larger than 2 by 2, and we could have the case where the nullity can be 2, because when we're trying to get the initial equation, we mean this equation. If we're trying to get the reduced row echelon form of this, we could end up with 2 free variables, and with 2 free variables, that means that the nullity of the space regarding a specific eigenvalue could be 2, it could even be 3 or more. And in today's class, we're going to see the number of eigenvalues and the number of eigenvectors associated to these eigenvalues. It is very important for us to determine whether a matrix is diagonalizable or not. Okay, thanks, Ari. Any question for what we did so far? Okay, if there's no more question, we can stop this session, have a short break.